All right. I think we'll get started as people continue to filter in. Welcome everyone to this first Scope webinar of the year. We're very happy to kick off this year's webinar series with someone that I've had the pleasure to work with over many years, Dr. Mary Monty from the University of Iowa. Dr. Monty obtained her PhD in 2014 in electrical engineering from the University of Rochester. From there, she joined the Magnetic Resonance Research Facility at the University of Iowa as postdoctoral fellow working at 7T for multi-shot diffusion MRI. And in 2019, she became assistant professor in radiology at the University of Iowa Carver College of Medicine. She's worked on a number of projects, including joint KQ accelerated diffusion MRI and a method called muscles, which allows for the recovery of high resolution diffusion images from multi-shot acquisitions without the need for navigators or explicit phase compensation. Today, we're going to be learning about her latest work in model-based diffusion MRI. And with that, I hand it over to you, Dr. Monty.
Thank you, Cam, for the introduction. So as he mentioned, today I'll be talking about model-based deep learning for accelerated diffusion MRI. So I will start with a brief motivation and talk about why we need to accelerate diffusion MRI. And so let's start with what we are actually measuring in diffusion MRI. So most of us here already know what diffusion MRI is. It's a non-invasive neuroimaging tool that has been used extensively to study brain microstructure and connectivity. And we all know that it doesn't require any external contrast agents. The contrast comes from our signal present in our body itself, specifically the microscopic diffusing motion of water molecules that are present in our cell membranes. So you can visualize this microscopic diffusing motion as a random walk in 3D space as shown in this simulation, but the same thing is depicted in this picture here, which shows the diffusing motion of the water particles in the cellular spaces. As you can appreciate from this picture, depending upon the packing of the cells in the tissue, the way the diffusion motion happens in between the cellular spaces get modified. So if the cells are loosely packed in a tissue, then the diffusing particles are free to diffuse within in the cellular space, whereas if the cells are highly tightly packed, then they are forced to diffuse along this tissue boundaries, resulting in a highly anisotropic diffusion. So if we can characterize the amount of anisotropy present in the in a voxel, then it gives some highly important information about the underlying microstructure, and this information has been used extensively in the past to study in vivo brain connectivity as well as white matter integrity. It is also important to appreciate the length scales of these measurements. So during a typical diffusion measurement, it takes about a few milliseconds to generate the contrast, and during that time the water molecules are only diffusing the mean free path that the water molecules cover over that small time period is on the order of micrometers. So essentially we are getting some very informative micro level information from these measurements. So basically we have a microscope in our hand to study the tissue information using the diffusion MRI. So that opens up some exciting prospects. So we can now talk about things like in vivo histology. So these are the images that I have taken from the recent paper in NMR and biomedicine, which shows that we can get similar information similar to a classical histology from microstructure imaging. So as we all know, classical histology has several disadvantages. It's an invasive technique, it destructs the cell. But if we can do in vivo histology, then we can start thinking about looking at the cellular level information in vivo without having to kill the tissue, which has a lot of implications in understanding the human physiology or the brain physiology. So microstructure imaging using diffusion MRI, there is a great motivation to pursue that research. The prospects are great. So how far are we along in achieving this goal? So unfortunately, in MRI, there is a fundamental limitation associated with the spatial resolution of the MRI images. So in MRI, our voxel sizes are really big. So we don't have as much anatomical detail that a classical histology has from these MRI measurements. In other words, we suffer from severe partial volume artifacts. So how can we even think about doing microstructural imaging using MRI measures? So one approach, of course, you can try to improve the spatial resolution of MR images, which is one approach. A complementary approach would be to depend on model-based approaches. So the idea behind model-based approaches is that if you can come up with very accurate models for these tissues, and you can accommodate as many tissue compartments into those models, and you can accommodate as many biophysical processes into those models. And then if you can also come up with measurements that has relevant information to separate these compartments and the biophysical processes, then you can think about fitting those measurements to your model and then extract the histological information that you are interested in. Of course, the problem with this approach is you need to come up with accurate microstructure models. That itself is a challenging problem, which I won't be talking about in this talk, but assume or suppose we can come up with such biophysical models. So here I'm showing an example that is already published in the literature. So if we can come up with a tissue model such that we can compartmentalize a tissue into, say, a few, here 3 different compartments, then we can assign specific diffusion properties to each of these compartments and try to come up with measurements that can provide or separate these different parameters that are present in the model. But even this problem, you can start to see how complex it is, because we want to come up with as elaborate models as possible in order to get these highly specific microstructural information. However, that means that we now have a lot of unknowns to solve for, and because of that, we need to have a large number of measurements. And the kind of measurements, we don't even know what kind of measurements we would need to solve that problem. Probably we need to sample in multiple dimensions, because the model is a nonlinear model that we are trying to solve. And if we don't have enough information to separate out these compartments, we may end up with multiple solutions for these models also, which will be the purpose. So basically, we need a large number of measurements, at least in 2 complementary 3D spaces that we already know, which happens to be the K space and the Q space. So diffusion imaging is usually referred to as a KQ sampling problem, and I'll talk about both the K space and the Q space a little bit. So as we already saw, MRI is fundamentally limited by its spatial resolution. So if we want to overcome the partial volume effects, we need to improve the spatial resolution, which means we need to improve the K space coverage, which is the frequency domain or the data sampling domain in the MRI acquisition. But increasing the K-space coverage is not an easy task, because as we sample more K-space points, we increase our echo time in our acquisition, which leads to low SNR, leads to artifacts. So we don't want to increase the K-space coverage such that we compromise the image quality. So the solutions are, we can go for either improved pulse sequences or for improved hardware with high slew rates, or we have to rely on accelerated acquisitions that acquire only a few k-space points. So the second complementary space that we need high resolution in is the Q space, which is the space that characterizes the anisotropy present in our measurements. So high Q space coverage would mean you need high angular resolution and multi-shell sampling, which is illustrated in this cartoon here. So this cartoon shows that if you have fewer angular samples, then you risk the chance of mischaracterizing the anisotropy, and then all your analysis will be affected by that wrong information. Similarly, you need to have high or multi-shell sampling, which improves your sensitivity to the diffusion displacements. So you need dense coverage both along and within each of the shells. But this is challenging because as you collect more samples, you are increasing your scan time. Also, as you go for high B values, you have a long echo time, again limiting the SNR. So again, the solution is either go for improved hardware that can provide high G max, or go for accelerated acquisition where you somehow collect fewer samples but reconstruct more samples than you collected. So to summarize, for improved microstructure mapping, we need to address the spatial resolution issue as well as the Q space coverage issue. So we are talking about a 6D sampling problem here in the joint KQ space, which leads to prolonged scan time. So acceleration techniques are inevitable. So let me cover some of the basic acceleration methods that are already available and many of which you are already familiar with. So I'll just skim through them very quickly. So the first method that we are all familiar with is the parallel imaging acceleration, which basically instead of sampling all the k-space lines, we are only going to sample some of the phase encoding lines and then try to fill in the missing k-space data using some model-based reconstructions. So the common reconstructions used are sense and grappa. So basically, these reconstructions, the model-based reconstruction, take into account the acquisition physics into the reconstruction and are able to do a more sophisticated reconstruction than a simple fast Fourier transform and come up with the unaliased images. But this technique is used mainly to accelerate the k-space sampling. The problem with this method is we know that the acceleration that it provides is very modest, around a factor of 2 to 3. A different type of parallel imaging acceleration now that is commonly used in diffusion imaging is multiband acceleration. Here also you need a specialized pulse sequence and a specialized model-based reconstruction that will accommodate the physics that is involved in this multiband acquisition. The multiband acquisition helps to reduce the number of TRs, so it helps to improve the Q space coverage. Again, this method can also provide modest acceleration, about a factor of 2 to 3. And I would like to point out at this point that we don't usually combine multiband imaging with the k-space undersampling that I discussed in the previous slide. That's mainly because the model-based reconstruction rely on the same information to reconstruct these two undersampling problems. So there is not enough information to give a very good reconstruction. So if you combine multiband imaging with parallel in-plane acceleration, then you might end up with noise amplification or loss of SNR. So another acceleration technique that is available in diffusion MRI is compress sensing, which primarily has been used to accelerate the Q space acquisition. Again, compress sensing relies on a regularized reconstruction using some constraint to reconstruct the undersampled Q space data from the Q space domain. In compress sensing, the main constraint used is the sparsity of the diffusion signal. So which has a form as shown here, usually imposed using a L1 normalization or L1 minimization. So the sparsity can be imposed either directly on the diffusion signal, or it can be imposed using sparsity in some other transform domains also. Again, the way it accelerates the acquisition is it helps to reduce the number of TR, so you can go for more Q space coverage within the same time. Again, in its simplest form, the acceleration provided by compress sensing is also very modest. But you can combine compress sensing with parallel imaging and can go for higher acceleration. Again, in that setting, we can now think about accelerating in both the domains, the K domain as well as the Q domain or the joint KQ domain. Again, here we rely on model-based reconstruction and make use of some constraints, either in the K space, Q space, or in both the spaces. So the commonly some techniques that already make use of these regularized model-based reconstruction for compress sensing and parallel imaging are the L1TV, the joint spatial angular sparsity methods, and the dagger method. I won't go into the details, but you can refer to that. Anyway, these methods help to achieve higher acceleration, but the disadvantage is that these methods are highly computational when it comes to the reconstruction. And many of the compress sensing methods make use of very large dictionaries. Very large dictionaries usually help with improving the accuracy, but they result in long reconstruction time. So that's the main disadvantage associated with these methods. And another acceleration technique that now we are all too familiar with is the deep learning methods. And out of the many methods, the Q-space deep learning method, which was introduced early on in the field, really caught the attention of the field because it proved the power of machine learning to accelerate diffusion MRI. So along that lines, many different methods have come up, but the basic idea remains the same. You make use of a neural network to learn some mapping. So if you have fully sampled data and you can come up with the features of interest that you are interested in reconstructing, then you can use that features of interest and learn or train a neural network such that the input is the undersampled data and the output are the features of interest. So the neural network will learn that mapping and will help to accelerate the acquisition. So the advantages with these methods is that it can provide very high acceleration, and also another big advantage is that the fast reconstruction that these methods enable. But as the field has matured, we know that this method also has several disadvantages. The main disadvantage being that these deep learning methods do not generalize to all the settings where the learning was not performed originally in. So the learning is highly contextual, which means that it can provide inference correctly in the situation where it was learned, whereas if it doesn't, if it was not trained for some particular situation, then the results are probably not trustworthy. So overfitting is hard to detect. So because of that, it's hard to generalize these methods to study or the general population. The other disadvantage associated with these methods is that it has very demanding training data constraints. So that brings us to the topic of our discussion today, which is model-based deep learning. So the main idea of model-based deep learning is to combine the advantages of the model-based reconstruction methods and the deep learning methods. So in model-based methods, the main advantage is that the method can be generalized to any acquisition setting. So we take into account the acquisition physics into our reconstruction, so that if we want to modify our reconstruction to a new setting, then we simply need to modify our encoding operator, and then we can adjust that to any acquisition setting. So if we want to change the sampling pattern, the amount of acceleration, noise levels, any of these things, model-based reconstructions can be easily adapted to any of these settings. But the disadvantage is that they are highly computationally complex, especially when you're using some sort of regularizations. For example, the L1 based recovery is going to be highly computational. On the other hand, the deep learning methods, the main advantage is the fast computation, but the disadvantage is the generalizability. So if we can combine these two methods, then we have a very good formulation to accelerate our diffusion KQ space sampling. So that's the goal. So our approach is to make use of the deep learned priors as a constraint in our model-based reconstruction. So in the coming slides, I will show how we can make use of this concept to accelerate the joint KQ space of diffusion MRI, and then I will also talk about the generalizability of this method to various arbitrary settings, and also how we can achieve very high acceleration and fast computation. So for that, let's look at the problem of the joint KQ acceleration. So here I have I'm showing the cost function for a traditional compress sensing and parallel imaging based joint KQ space acceleration. So here we are talking about the joint recovery of all the Q space points. So because we want to push the acceleration to the extreme levels, we are making use of many regularizers. So we have a spatial regularizer as well as a Q-space regularizer. The spatial regularizer, in this talk, I'm going to just assume that it's going to be a TV regularizer, not very important in this talk, but what we are going to focus is on the Q-space regularizer. So in the compress sensing setting, the Q-space regularizer is going to make use of the sparsity prior of the diffusion signal. And although the sparsity prior can be imposed on the transform domain of the diffusion signal, it is also possible to make use of sparse diffusion models directly into this formulation. The advantage of such a setting is that then in that case we are directly reconstructing the features of interest that we are interested in. But in diffusion MRI, we don't have a lot of models that are already sparse in its natural form, but it's been shown that we can sparsify any arbitrary diffusion model by just discretizing the model on its individual parameters and then making a big dictionary where the atoms of the dictionary are the discretized combinations of these parameters. So then the L1 regularization becomes a problem of finding the best linear combination of atoms in the dictionary that can predict the signal that we are interested in reconstructing. But the problem with this approach is that we will end up with a large dictionary size, and then solving for this L1 recovery in every voxel, especially from undersampled multi-channel data, becomes a computational nightmare. So it's going to be very hard to solve that, or it's going to take a long time to solve such problem. So what we are going to do is, instead of that L1 regularizer, we are going to replace that with a different Q-space regularizer that was learned during machine learning. So here I have a new regularizer P of theta, which is defined as shown here, which is where S is the Q-space data and d theta is a neural network that has pre-learned, or that provides a Q-space prior from deep learning. So the advantage that I want to achieve from this method is that because this is a pre-learned regularizer, I can put that in my reconstruction in a plug-and-play fashion. It's going to provide me with fast Q-space regularization. The dictionary size would not affect my reconstruction speed. Similarly, the dictionary discretization accuracy also would not influence my reconstruction accuracy. So how can we do that? So here the pre-learned Q-space prior, what exactly is this pre-learned the Q-space, or what exactly is machine learning in this context? So here we have this neural network d theta that will try to pre-learn the relationship between the Q-space samples that we are going to reconstruct. So for that, we will make use of a denoising autoencoder neural network. And what it's going to do is it's going to learn a compact representation of the manifold over which all these samples exist. And that compact representation provides us with a prior information that constrains our reconstruction to come up with the solution from this undersampled data. So a brief review of the autoencoder neural network. It's a special kind of neural network that learns to recreate the input. So if you provide an input to this kind of neural network, the output is going to be the same as the input. It has two main parts, the encoder part that takes the input and compress it into a lower dimensional code. And then there is a decoder which takes that code and recreates the output. So the code is also known as a latent space representation. So denoising autoencoder is a special neural network where the input is a noisy data, but the output is a denoise or the noise-free version of the input data. So in our case, we are going to train the autoencoder neural network using the Q-space sample so that this network learns to recreate the Q-space samples that we are interested in reconstructing. So how do we bring that into our model-based reconstruction? So remember, this is a joint reconstruction. We are trying to reconstruct all the Q-space points. So we start with the highly undersampled K-space data from all the Q-space points. We do an initial model-based reconstruction that imposes the data consistency using the acquisition physics. Then the estimate that comes out from that model-based reconstruction is of course going to be noisy, but we can pass that to our pre-trained denoising autoencoder neural network, and it can provide us with a predicted Q-space signal that belongs to the subspace where we want to reconstruct it. So based on that new update that the denoising autoencoder provides, the model-based reconstruction goes back to the measured data and come up with the new update that satisfies the data consistency term. So in order we can visualize the reconstruction as follows. You start with the undersampled K-space data, do an initial model-based reconstruction, come up with a noisy estimate for the Q-space signals. We already know the manifold on which our Q-space data is supposed to belong. So for every voxel, you project the Q-space data from that voxel onto this manifold and then compute the projection error. Okay, so the p theta is the projection error from the manifold on which the data belongs. And we are going to incorporate that projection error into our cost function. And the goal of our reconstruction is to find the solution that minimizes this projection error to the pre-learned manifold. And we can solve this cost function using solvers such as plug-and-play ADMM methods. So we saw that if we can pre-learn the plug-and-play prior, then it can provide very fast Q-space regularization. But the catch is that we have to pre-learn that Q-space which we are interested in reconstructing. So that means we need to know beforehand the b-value and the sampling points that we are going to reconstruct to. So once we know the b-value and the sampling points before for pre-learning, then we have to find appropriate training data to do that pre-learning. So the training data doesn't have to satisfy a lot of constraint. As long as you have the b-value and the sampling point match, then you can find any training data that satisfies that constraint. It doesn't need to match any other parameters. For example, you don't have to match the spatial resolution, the echo time, any of the acquisition protocol except the b-value and the sampling points. So you can use data from a totally different scanner, a totally different field strength, or from a totally different protocol that used. So the only constraint is to match these two parameters. So out of all these possible ways to get training data, one of the easiest and the most flexible option is to use simulations. So as long as you know the b-value and the sampling points, you can simulate the diffusion data using any method that you know. For example, you can simulate diffusion data using a simple diffusion tensor model, or you can go for more complicated diffusion models such as 2-compartment or 3-compartment or ball and stick or any such model. So let's say we start with this model. Then what we do to generate the training data is we discretize the parameters of this model, and then each combination of these model parameters form one set of training data. The Q space is fixed, we predefined it. So each set of the discretized parameters form a training data. So we generate as much training data as we need. So if we are using this model, then, and if we are going to use in a human study, then we have to change the parameters within the biophysical range, which we already know from the literature. So you generate your training data and feed that to your autoencoder network, which then learns to recreate the Q-space data that you are interested in learning. So you can see that now we are talking about the pre-learning phase. So the dictionary can be as big as you want, because the dictionary size is not going to influence the reconstruction. This only comes in the pre-learning phase. So you can use as much training data as you want. So I hope it's now a little bit clear how we bring in the pre-learned, deep learned prior into our model-based reconstruction. Once we pre-learn it, it can be incorporated into the model-based reconstruction as a plug-and-play manner, which provides very fast Q-space regularization. And I hope it's also clear why we can generalize this method to any sampling trajectory, because any of the change in the acquisition parameters are going to be handled by the model-based reconstruction part that takes into account the acquisition physics. It's only the Q-space regularization that is provided by the deep learning part, which we made it fast using that pre-learned prior. So one natural question would be, what happens when our pre-learned prior is different for the data that we want to reconstruct? Of course, we predefined our b-value and the sampling points in our training phase, which means that this particular trained autoencoder can only be used to reconstruct that particular b-value and the sampling points. It won't reconstruct any arbitrary diffusion data that we want to reconstruct. The main reason is that, as you can see here, the input points of the autoencoder are defined by the number of Q-space samples that you have in the data. So suppose you train to reconstruct a 60 Q-space sample, then this autoencoder don't know how to reconstruct a 30 sample. Okay, so that's the main problem. But we can overcome this using this problem by a slight modification of our autoencoder formulation. So for that, we make use of the spherical harmonics idea. So spherical harmonics provide a basic framework to convert the sampling points in our spherical domain. So using the spherical harmonics basis function, it is very easy to go from a 60 sampling point to a 30 sampling point. So if we can, instead of training on the raw Q-space signal, if we can train our denoiser on the spherical harmonic coefficients of the training samples, then we can use that kind of autoencoder to reconstruct any Q-space samples that we want. So the only modification is, for the autoencoder part, we modify the autoencoder as follows, where we take the spherical harmonics transform of our diffusion signal, which will give us the spherical harmonics coefficients. And so the training data is the spherical harmonics coefficient of each of these samples. So we train the autoencoder on the spherical harmonic coefficients, which will provide us the capability to change between any Q-space sampling points. So again, so now we solved the problem associated with the arbitrary Q-space sampling points, but here the B value still needs to be predetermined. So if we train for a B value of 1000, then we have to stick with reconstructing a B value of 1000 for the testing data as well. But if you want to reconstruct arbitrary diffusion data from different V values, then it's very easy to train the neural network for a different V value, because the training process involved in all this is very fast. So it usually takes like 1 hour max to train this kind of neural network. So, and plus generating the training data is very easy. So there is no reason why you cannot retrain it for any number of B values that you want. So another caveat that another detail that I also want to mention is that since we are using this autoencoder for the undersampled recovery from the multi-channel case-space data, now we are dealing with complex data instead of magnitude data. So in the original setting that I was discussing, instead of training the autoencoder on the magnitude data, we have to train the autoencoder using complex data. And I can do that by simply modulating my magnitude data with different random phase, so that the training data is a complex data and it can handle the complex reconstruction from the multi-channel case-space data. Okay, now we'll take a look at some of the experiments and the results. So the first experiment deals with the acceleration of multi-shell data. Again, we are dealing with joint KQ acceleration. So we have a joint reconstruction setup, and because we want to push the acceleration to the maximum possible level, we are going to use a random KQ undersampling method. This can be achieved by randomizing the case-space trajectory associated with each of the case-space acquisition. So that's the basic setting for all the experiments that are being presented in this talk. So the first data comes from a 3T experiment where I have 1.7 millimeter isotropic resolution from 3 different shells, 60 points each. So I usually collect the fully sampled data, so I have a reference to test my acquisition to, and then retrospectively undersample the data to various acceleration levels. So here I am testing my data at 3 different acceleration levels. For moderate acceleration such as r is equal to 4, I only undersample in the case-space domain. So for all the 180 Q-space points that belongs to all the 3 shells are sampled, but the case-space is undersampled in each of these settings using a randomized pattern. In order to push the acceleration to higher levels, then I start skipping my Q-space points too. So here the case-space is undersampled. On top of that, the Q-space is also undersampled. For acceleration of 8 or acceleration of 6, I undersample 60 points, or I skip 60 points out of the 180 points. For acceleration of 8, I skip 90 points out of the 180 points. So let's take a look at the reconstruction results. So here I'm showing the multi-shell reconstruction that comes from a simple model-based reconstruction, the easy-sense reconstruction, and these are the results of the fully sampled case from all the 3 different shells. Now this is individual Q-space reconstruction, so point by point Q-space reconstruction. So now instead, if we use a joint KQ joint reconstruction of the fully sampled data, you can see that you get much better improved SNR and denoised results also. Now, if you look at the accelerator data, you can see that at 4 times acceleration, you can still reconstruct all these multi-shell data with very good accuracy. Now this is the results for the acceleration factor of 8. Remember, here we did not sample a lot of the Q space points, but the method can still reconstruct all those Q space points. So again, if we look at the Q space signal plot from this ROI, the blue curve is the fully sampled Q space from all the 180 Q space points. The red would be the measured data, and that shows points that were not sampled at all, but the reconstructed, the final reconstruction can provide the data that is in very good agreement with the reference data. So because this was a multi-shell acquisition, we can now look at the microstructural maps. So these are the orientation distribution index reconstructed using the NODI model. So fully sampled data, acceleration of 4 and 8, and these are the difference map for the accelerated case with respect to the non-accelerated case. Again, the neurite density index computed from all these accelerated cases, and you can see that the error is very low. So now we extend this method to also incorporate the multi-band acceleration. Remember, I said earlier that we don't usually combine parallel imaging with or in-plane acceleration with multi-band acceleration, but here we are going to combine that because we have this joint reconstruction that helps to improve the SNR in our case. So we are going to use a multi-band acceleration of 3 in all these cases. So this image shows the power of the joint reconstruction basically. So this is a individual reconstruction, a point by point reconstruction of the multi-shell data using traditional no model based, no deep learning in this method, whereas this is the Q model reconstruction from the fully sampled case. Basically this shows the SNR improvement that comes from the joint reconstruction as well as the denoising that's provided by the Q space regularizer. So this shows more results. So again, the first row corresponds to the fully sampled case from different reconstruction methods, whereas the second row shows the accelerated cases. So net acceleration of 12, 15 and 18 for the multi-shell data. Again, the residuals from these accelerated cases are shown, and you can see that the error from these reconstructions are very low. So you can again compute the microstructural maps from the NODI model. So the neurite density index is shown in the top row and the orientation index is shown in the bottom row. This is the result from the non-DL based, no deep learning fully sampled case. This would be the fully sampled case with the deep learning and the undersampled cases with the deep learning. And you can see that these maps looks exactly similar to the traditional no deep learning based methods. So now we extend this method to test data from a different field strength. So this is a 70 data just showing the generalizability to any field strength. So this was a healthy subject, but now we will look at the reconstruction from a subject that has a lot of lesions. So again, 70, we are using a multi-band acceleration of 2 in this case. So these are, this is a single shell experiment. So I'm showing the microstructural maps from a simple tensor model. So I have the mean diffusivity maps on the top row, the fractional isotropy, and the primary diffusion direction shown as color codes here. So this, the first column shows a traditional reconstruction with no deep learning, fully sampled case. The middle column shows the fully sampled but with the deep learning case. And you can see that the lesions are still preserved exactly as in the traditional model-based reconstruction. And now the last column shows the accelerated case reconstructed using the deep learning based method. Again, the lesions and its properties are well preserved in the accelerated case as well. So now we want to push it again to even more generalized setting. So this is an experiment done again on 3T on a subject with multiple sclerosis. Now we have multi-shell and multi-band acceleration, everything coming together. So this is a T2 flare data from the subject. You can see that the lesions are very small, very diffuse lesions in the subject. So what I'm showing here is the intracellular volume fraction maps computed from the NODI model. So the second row would correspond to the traditional non-DL based method, which was reconstructed individually, and then the NODI model was fit to those diffusion weighted images. You can see that the Q model or the Q-space deep learning method at various acceleration of RS equal to 3, 12, 18 all reconstruct these intracellular volume fraction maps equally good. All the lesion characteristics are still preserved in the highly accelerated cases as well. And finally, I also want to show the learning in the spherical harmonics domain. So here the test data is a single shell data, B value of 1000. We want to reconstruct 60 diffusion directions, but here in order to reconstruct this test data, I am using two different denoising autoencoders. The D1 was trained with a totally different Q-space sampling points, but it's still close to the 60. So I have 64 Q-space sampling points here in my training data. And then I'm using that denoising autoencoder to reconstruct the 60 samples, which is shown to reconstruct very well with very low error compared to the a denoiser that used exactly the same 60 points to reconstruct. Another denoiser, D2, was trained with a totally different set of Q-space points, so 90 samples, 90 Q-space samples during training, but again used to reconstruct the 60 Q-space samples. Again, you can see that the reconstruction works very well for this test data with very low reconstruction error. So with that, I would like to conclude. So I hope I have showed how we can combine model-based reconstruction with deep learning to come up with a very powerful reconstruction framework. This framework can be generalized to many acquisition settings, can handle arbitrary sampling trajectories or acceleration just like any other model-based reconstruction. But the deep learning regularizer can provide the fast regularization properties and can afford very high acceleration. So most of the results that I was showing were taken from these publications. So feel free to refer to that if you have more questions. So finally, I would like to thank you all for listening, and I would like to thank my team that has helped me with doing all these research, and also my industrial collaborators as well as funding agencies. Thank you.
Thank you. Excellent talk. So if for anyone who hasn't typed questions in, please go ahead and type your questions into the chat box. We're already starting to get some, so I'll just go ahead and read them out to you. And so first one is from Prashant. What is the minimum computing hardware required?
I didn't use any GPUs or anything fancy, just a basic desktop that I have. As I said, the training is not at all computationally intensive, so nothing fancy.
Excellent.
The reconstruction, the model-based reconstruction is all done in MATLAB. The training was done in TensorFlow. Again, very modest hardware.
Yep. Question from Dr. Birkin-Bilgic. Thank you so much for the talk, Dr. Mani. Do you think that any geometric distortions across directions due to eddy currents, where I'll add in any sort of field fluctuations, is a big concern for Q-space regularizers.
So basically, you are imposing a Q-space prior when you are doing a model-based reconstruction. So in the end, the reconstruction is primarily driven by the model-based reconstruction. So if you have distortions in your image and if you don't account for that distortion correction in your forward model in the model-based reconstruction part, then you would still expect distortions in your reconstructed image. So the Q-space regularizer is just providing a constraint to constrain our solution space, right? That's the only thing it's going to do. Anything, the geometric distortions and everything will still be preserved in the reconstructed images, which needs to be corrected later on.
Okay. Question from Sebastian Rosenvig. Thanks for the great talk. In the Q model images, you show extremely little noise. However, I guess the results also depend on how you choose the regularization parameter for the neural network regularizer in the minimization problem. How do you make sure you don't over-regularize the result compared to the data fidelity?
Again, this is a common problem we all deal with in any regularized reconstruction, right? So as long as you have your fully sampled data, then you can come up with a sense of how much regularization is ideal. So I don't use any fancy metric to come up with the regularization. It's just basically tuned based on trial and errors. So one other thing that I want to add about the Q-space regularizer is that while training the Q-space, the denoising autoencoder, I add noise at various levels. So this denoising autoencoder is trained to deal with a lot of noise levels. So that is another feature that is present, which I didn't mention during the talk.
Question from Hong Li. Thanks for the great talk. It seems the goal is to compress the dictionary using deep learning. Is this the correct understanding?
The goal is to come up with a compact subspace which can be used to constrain our reconstruction. So if you have the Q-space sample, if you have a lot of Q-space samples, then the autoencoder is good at compressing that and coming up with a nice compact representation of the manifold on which that samples belong to, which we use as a constraint in the undersample reconstruction.
Thanks. A question from Dr. Bertram Wilm. Great talk and impressive results. I have quite a general question on the application side. For which application do you think your method could make the biggest difference or enable a new type of diagnosis?
I haven't thought a lot about that. Of course, when the results from the multiple sclerosis subject turned out to be very good, it definitely was exciting for us. So now it at least tells us that we can now use it to study, the diseased characteristics from these using these multi-shell sampling so that we can apply the complex the biophysical models to study those disease characteristics. It's definitely exciting, but I really haven't thought about a unique application that it's going to enable. Probably not the greatest answer, but yeah.
Question from Dr. Lars Kasper. Thank you for the very instructive talk, Dr. Mani. Deep learning regularization rests on the assumption that the space of the diffusion images S is indeed a low-dimensional manifold. One could imagine that when adding more and more diverse training data, this manifold approaches the dimensionality of the original data, the original space itself. Do you have any methods to check the dimensions of that manifold that the network learns that could inform your max possible acceleration?
So I think based on the models that we have, we can already infer that we can definitely come, or again, based on the models so far that we have, like for example, the three compartment model, I think there are only a few independent parameters in that model. So we can assume that there is going to be a compressible latent space if we are going to work with that model. Of course, if you come up with a more complicated model, that situation will change. But for the models that we currently have, I think if we have a lot of Q-space sampling points, we can definitely compress it to the a lower dimensional subspace.
Okay. Sounds good. See. And David Bruner, thanks you for the informative talk. Can you comment on the impact of microstructure estimation of inconsistencies between acquisition? For instance, different distortions per diffusion direction or strength.
Again, the Q-space regularization itself will not correct for any of those problems. If you can accommodate any of that in the forward model, you can correct for that. Otherwise, you have to independently correct for all of that. I don't know if I answered the question that you were asking, but feel free to reach out if you still have unanswered questions.
Yeah. Sounds good. Seeing no more questions, I'd like to thank you for your time and for this excellent presentation. It's always great to see what you're doing in advanced diffusion reconstruction. That's it. Thank you for your time, and thank you everyone who attended for coming. We appreciate it greatly. And everyone have a great day.
Thank you so much.